Hi, my name is Zhang, and my research is about synthesizing new bicyclic organic compounds by photocatalytic reactions. So what I'm going to cover today is an introduction on photocatalytic reactions, my hypothesis, my experimental designs and results, my conclusions, and further studies. So you might be wondering, what are photocatalytic reactions? Photocatalytic reactions are reactions that use light energy as a means of synthesizing new compounds. These reactions were largely inspired by photosynthesis, which is the natural phenomenon where plants use sunlight and carbon dioxide and water and convert it to glucose, which is a form of chemical energy. So in 1912, the scientist Siemessian tried to do the same thing for chemicals. So he placed lots of chemicals in vials and exposed them to sunlight, and he wanted to see if they undergone new reactions. Although he was initially unsuccessful, he opened up the bridge of photochemistry. So, in the past 5 years, chemists have discovered that using a catalyst can make these photocatalytic reactions work. So they were using alkenes, which are carbon-carbon double bonds, as you can see right here, 2 horizontal bonds. And they form radicals, which are molecules that have unpaired electrons, and they're highly unstable because they have a nuclear charge. So they would readily undergo other reactions to become more stable. However, we're trying to expand the scope of the reaction to alkynes, which have never been done before. Alkynes are these compounds right here, which is a carbon-carbon triple bond, where you can see 3 horizontal lines stacked on top of each other. And we want to see if they also form radical intermediates. So this is our alkyne that we're going to be using for our hypothesis. We're using this alkyne. What's special about it is that it has a radical acceptor right here. So radical acceptors can stabilize radical intermediates because some molecules are more stable with radicals than others. In this case, this compound is more stable because it is resonance stabilized. So we reacted with pyridine and oxide, blue light, and a photocatalyst. And as you can see, the radical initially started on this triple bond, but then the radical acceptor trapped that radical, and then it eventually goes on our radical acceptor because it's more stable. And in the process, it forms this bicyclic ring structure. A bicyclic ring is a 3-membrane ring fused with a 5-membrane ring. And we had 87% yield with our product, which is a pretty decent yield. So this reaction is useful because it can be used to synthesize biologically important drugs. One such example is milnacipran, shown right here. It's a useful antidepressant, which can be synthesized with our strategy. So previous research to synthesize milnacipran and other important drugs used expensive gold or rhodium catalyst. That's a pharmaceutical concern, as metal residuals may always still be present in the drugs. And our strategy does not use any metal at all to synthesize our desired products. So that's 1+ for our reaction. So our experimental design, we start out with the alkyne, which is this compound that we synthesized. And then we use pyridine and oxide and a photocatalyst to help absorb the light energy. And then we synthesize our bicyclic compound. As you can see up in the top right corner, this is our reaction. We place it in a cardboard box and we expose it to blue light for 24 hours. We place our chemicals in these vials, and it's being stirred continuously with a stir plate to facilitate even stirring. So after 24 hours, we would take the chemicals out of the vial and we would try to isolate our desired bicyclic compound. So after we've isolated our compound, we want to make sure that we synthesize the right compound. One way to do it is an NMR spectroscopy. NMR spectroscopy basically looks at the chemical shift of each hydrogen atom on the molecule. Every single molecule in the world has a distinct NMR spectrum, so we can use it to confirm our desired products. For example, right here, these 2 hydrogen atoms, we can match it to the peak right here. So this peak matches those two hydrogen atoms. And we could do the same thing for every single hydrogen atom. And this NMR spectrum shows that it matches our predicted structure. So we've synthesized the right compound. So after we've done it for that one reactant, we synthesized a wide variety of alkynes, and they all underwent our radical reactions, and we had a 70 to 90% yield on each of them. So that synthesized, that said that our strategy was very efficient and effective. So our conclusion is that we had a successful metal-free synthesis of bicyclic compounds. We did not use metals in any of our steps. And as a result of metal-free, it's cheaper and more sustainable synthesis because it can be used for drugs like milnacipran, and our strategy works for a wide variety of alkynes. For the future, we're going to try to change our radical acceptors. In this case, we use this as our radical acceptor to synthesize this compound, but we could change our radical acceptors like the methyl group, the epoxide, amine, and we could change our radical acceptors, and we'll each probably get, what we propose is that we'll get these different compounds by changing our radical acceptors, and we can use that to synthesize a wide variety of more useful products in the future. I would like to thank my mentor, Dr. Zhang, for letting me allow to participate in this research, and I'd also like to thank my group mates, Jonathan, Brad, and Steve, and I would like to thank the ACS Petroleum Research Fund for funding our research. Thank you, everyone. Thanks for listening.